Alright. Yeah, so as you all know, my name is Sean Casey, and I work in the same lab as Blake, Mechanical Engineering. So I'll be talking today about hydraulic power transmissions, or point absorber wave energy converters. Specifically, we'll be looking at a passive hydraulic power takeoff topology, and one that is actively controlled. We'll do some simulation and modeling and look at some results, and then see how those results can give us an insight into what kind of loads they might see and the differences, and qualitatively the differences between the two topologies. Then we'll wrap it up with some conclusions and future work. So as this slide shows, many companies out there right now are investing in hydraulic power takeoffs. They're basically they're plug and play devices. You can suit them to whatever kind of needs you have as a developer. They're heavily engineered. They're just and they've also got very high power to weight ratios, which make them attractive. Before I begin, I just want to differentiate what I mean by a passive versus an active system. So as a passive system, as you can see, the parameters are set beforehand, whereas an active system senses, thinks, and responds to its environment to maximize some kind of performance measure. And so the motivation behind this, there's a lot of talk about always going after every bit of power that you can in the ocean, but is that really what we want to do? The ocean can have wave forces that are orders of magnitude higher than what you would see nominally. So, so is it the best to always actively control something, or can it be better to just set the device out there and let the mechanics take care of it? So, modeling approach, you just take regular and irregular waves, develop an excitation force with a hydrodynamic model of a point absorber buoy, model a passive hydraulic power takeoff system, and then another topology which is actively controlled, and then we do some analysis on this. So to go over the different configurations here, this is the passive power takeoff system. We have a cylindrical buoy. We have a double-acting piston pump. We have a set of rectifying check valves that take the bidirectional flow from the pump and make it into unidirectional flow. There's a set of accumulators that provide energy storage and power smoothing. There's a hydraulic motor that's set for the wave state, or C state, that it's operating in. And then we have a generator. It's modeled as just a simple linear generator, a linear damper. And so the passive hydraulic system, as the buoy is forced up, the side A is pressurized, goes over check valves 1 and 3, and then as the buoy moves down, the opposite side is pressurized, and the opposite check valves are used. And so you still have this high pressure side of the C, and the low pressure side, D. For the active hydraulic system, we use the same buoy. These are the same parameters for the buoy. So then we use the same size pump, double-acting piston pump. We have a charge pump on here, and that's to replenish the flow. We have a variable displacement hydraulic motor pump, and this is the key ingredient here. It's able to change its displacement from positive all the way through 0 to negative. So an alternating pressure source can have a unidirectional rotational motion. So as the buoy moves up, we have side A pressurized. We have a positive displacement that's controlled on the pump, or the motor. And then as the buoy moves down, you see the opposite side is pressurized, but we control the motor such that the displacement moves to a negative displacement. We still obtain a rectified rotational motion. So the functional comparison, we can see the passive system. It's an open loop system. It's basically input to output. The key ingredients here are the rectification valves, check valves, and these accumulators that provide some energy storage. The active system is a closed loop system. We use a linear quadratic tracking controller to track an optimal velocity profile, and this optimal velocity profile will allow the device to achieve maximum power. The key ingredient here is the variable displacement hydraulic motor pump. So, and the generator is also, the damping on the generator is assumed to be able to be changed in order to provide some torque feedback as well. So in regular waves, again we did 3 meter and 10-second waves. And like Blake said, it's an attempt to allow some kind of representative wave environment of what you might see in Oregon. So the passive system in the regular wave environment, you can see this as it stalls out a little bit here, and I'll get to that and why that happens a little bit. But if you've ever heard of latching control, it's almost like it's reminiscent of that. So then the active system, since we're controlling it and we see a smoother profile here. Now the forcing that we see, and this is the forcing on the piston pump here. The forcing profile for the passive system takes on this square wave-like nature, and then the peaks are plateau, and that's due to the effect of the accumulators in the system. The active system has higher peaks, you can see right away, and also a smoother profile. So in irregular waves, this is irregular wave spectrum with significant wave heights of 3 meters and significant periods of 10 seconds. This is a 60-second window that we see. We see the active system is following this, it's at least in phase with this optimal velocity, whereas the passive system at some points can get out of phase, and then at some points it actually stalls out when there's not enough excitation force. And again, we can see the square wave nature of that forcing profile compared to higher peaks and smoother profile for the active system. Now, this is for the passive system. I just want to show what's going on here when it's stalling out. And if we take a look at the system pressure, you see the blue and green lines are side A and B here, and this red line up here is the high pressure side. In order for fluid to flow to the high pressure side, it needs to overcome the pressure in line C. We can see here that it's not able to do that, so fluid gets trapped on this side A and B here. And because it's modeled as slightly compressible, it has this spring-like effect where we have this high-frequency oscillation until it dies out, until there's enough excitation force for it to open that check valve. So here's the power comparison of what the simulations showed. So the passive and the active system were tuned to have the same efficiencies or input to output efficiencies, so mechanical over what you would see from the generator takeoff. And then in irregular waves, we see these values here. And this is a plot of the irregular wave power output of the two systems. You can see the blue line is the passive system. It has a much smoother profile, whereas the active system has much higher peaks of power, or power to peak ratios. So, and we see this higher efficiency that shows up, right? But this is indicating if all the parts are the same, all the efficiencies of the individual components are the same, this higher value is indicating that more reactive power is being used. So, and these are the power equations, or average power equations. So the mechanical force is that force in the piston, and the velocity of the buoy, whereas the generator is the torque on the generator, and the rotational velocity. So now the loading comparison. The methodology used here is take a irregular forcing profile that we've obtained in a 30-minute simulation, conduct a rain flow counting algorithm, and this allows you to count the number of irregular cycles. There's a standard out there for it. It's a common algorithm to do this. Then we count up the amplitudes of the cycles. Then we normalize these amplitudes as a basis of comparison for the two systems to their mean amplitude in regular waves, right? And then we create these loading histograms. And so the reason for doing this, it provides a way for you to see right away the qualitative aspects of these forcing profiles, so you can look at what your design requirements might be to protect against fatigue damage, fatigue failure. So for the passive system and the active system on the piston side, we show these two histograms. We see the passive system has much higher number of cycles, or higher frequency, whereas the active system has a much wider distribution. And that makes sense when you think about the forcing profiles that you saw earlier, how the square wave, or the accumulators, they limited the forcing on the piston side. And then on the generator side, we see almost an opposite phenomena here. Well, not opposite. Well, we have higher number of cycles for the active system versus for the passive system, and that makes sense if we see that in that last slide where we were showing the power between the two systems in irregular waves, that generator power for the passive system was much smoother and averaged out versus the passive system, which had much higher peak loadings. So these are kind of the visuals you can see with this methodology. So, and then the question you might ask is, where would you design your endurance limit? And if you divide these by the component area, or cross-sectional area of that particular component, you'll get a stress. And then that stress will tell you, how big do I need to make this component? And so we play it conservative, or we take a little more risk. Are you able to do that? See higher forcing profiles. So these are some of the answers that can be, or some of the questions you might ask when you look at these. So in conclusion, we modeled two hydraulic power takeoffs that are common in the literature. The passive system was tuned to the particular sea state, or the active system used the tracking control to get that optimal velocity profile. Passive system had higher frequency components, lower amplitude, and lower variability overall, whereas the active system had lower frequency and just kind of the opposite. So future work, we're going to be looking at other sea states around that 3 meter 10 second sea state, and develop a matrix of this so you can see right away how how it changes as you enter different sea states. Also, look at different systems. We showed a completely passive system and a completely active system, but are there synergistic effects if you put them both together? Can you get a better gain? Also look at other control techniques. We used a simple linear quadratic tracking controller, but there are other more sophisticated controls that might be able to, where you might be able to balance damage that you might see or actuator limits in the control strategy directly. So, just want to acknowledge funding for this. US DOE and NIMRIC, of course. And then I'll take any questions if you have it. Thanks.
I have a question about your efficiency calculation. How did you derive that?
So the efficiencies were basically, I call them efficiencies, but we're not modeling any efficiencies per se, like from the hydraulic component. It's basically this hydraulic power, average power over generator average power. So it's not a true hydromechanical efficiency that you'd see in like a motor pump or something. So it's basically it's an indicator, more qualitative indicator. So does that answer the question? Anybody else?
Can you go back to the regular wave time history? Okay, so is the inertia of the hydraulic system accounted for, or is it purely considered a damping force?
So the inertia of the fluid, you mean?
Well, yeah, essentially. I mean, the whole hydraulic system.
So let me just go to the forcing or the equations used here. So the equations for the buoy, we see the force of the PTO is basically the difference in pressure between these two sides, and that gets coupled. And this is the change in pressure, so you can figure out what your instantaneous pressure is in the two sides, and that way you can see the force on the.
So that's a function of z dot, right?
So yeah, it's a function of your of how fast the buoy is moving up and down, right?
So if you go back to the time series, time history, then I guess what I'm looking for is why aren't there 3 dominant periods in the time history? The first being the lump mass natural frequency of the buoy, the square root of k over m with the restoring force.
Right.
The second being basically the inertia of the hydraulic system.
Okay.
And I guess, I don't know, maybe just 2.
Yeah, so the inertia of the hydraulic, I'm not sure. Well, it is modeled as compressible, so there is that compressibility, but the inertia of the fluid itself is based. Yeah, it is that compressibility term. If you look at this equation, this is your inertial term from a fluids perspective or a hydraulic fluid perspective. I think, yeah, because this is. So I'm not sure if I understand.
Yeah, I mean, it's a really, really poorly posed question. But yeah, I mean, basically, shouldn't there be 3 dominant periods in the regular sea time history? One being the excitation force, one being the square root of k over m, the heaving natural period of the buoy, and then the third being the actual inertia of the hydraulic system. Now, the inertia of the hydraulic system may be really, really, really tiny, and so it doesn't really matter.
Yeah.
But
So-
why aren't there 3 dominant periods in the time history? I mean,
I'm not quite sure. So
yeah.
maybe I'd have to talk with you after and just kind of sense make. I don't know. So so 3 dominant periods. You mean in the forcing here?
Yes, enforcing. And they may be there. I mean, the square wave.
Oh, okay. So do you see? I guess this ripple right here.
Yeah.
If you zoom in on that, we will see another, and that's the generator turning and the fluid going from one side to the other. And you do see a very high frequency. I mean, not high frequency, but it's very low amplitude, I guess.
So
Is that?
yeah. I mean, like I said, it's a really, really poorly posed question because I'm not exactly what I'm looking for either. But so basically, the excitation force is still dominating all of the other components.
Yeah, absolutely.
How did you take into account mooring, if at all? Like the
Um,
damping, the everything is just still?
Yeah, it's assume that the hydraulic PTO is your mooring, basically, so that you can think of it as the
It's not
hydraulic
moving.
PTO. Yeah, it's not moving, so neglected, basically. But yeah, so there's no auxiliary mooring system in their model. So
Have you compared this against some of the work? I don't remember the researchers' names now.
I
But
have
basically,
looked,
they
I have
have-
looked at literature and seen these effects, seen forcing profiles that are similar to this, and also this kind of pseudo latching control that was observed. So yeah, I mean, I have done my best to validate it through the literature, basically. We don't have a model for this, or an experimental model for this.
Yeah, there was a group, it was some European country now, I can't remember, but they used a spherical buoy.
Uh-huh.
And basically the PTO that you've talked about here is exactly what they had.
Great.
And they did some.
Oh,
some
okay,
at-sea-
yeah, that's actually Waystar in Denmark.
Okay.
Yeah, so they did some design modeling. They used the model to tune or optimize their design. Yeah, that's this one. Yeah, and that's what that model, that PTO model is based off of.
I was thinking of a slightly different one, but.
Oh, maybe,
about it.
yeah, maybe perhaps. Yeah.
Yeah.
But, yeah. Anybody else? We all good? Okay. All right, well, I guess that's it. So next one's in 2 weeks. I think we already have a speaker lined up, so I think I have one more spot left if anybody is interested in presenting.